Hello everyone and welcome. We are the Lightning Group and this is our DP3 Rube Goldberg machine presentation. I'm Matthew Ray, this is Heather Hawley, and that's Sam Buck. The DP3 presentation report takes you through the latter half of the design process. We're focusing on designing the product and manufacturing the product. So we're going to walk you through the steps from project planning to critical assessment and possible future improvements. So we're going to go from what are the concepts and choosing a solution for our project to how could we have done this better in the future.
And looking at the Gantt chart, you can see the necessary steps that we needed to take in order to complete our Rube Goldberg design process. Anyways, from our DP1 report, we've changed a few things in the Gantt chart because we realized that not all things would line up the way we planned. So that's where our Gantt chart comes into play.
We conducted our concept generation methodology exactly 3 times, once for each different station. Each time, all 3 team members submitted a CAD model of their idea of a solution for the station, and we used several constraints to narrow down our options for those solutions. Our first was size, so we knew how much of the pegboard for each station we had allotted to use for that particular station. We also had decided initially that our stations would connect directly to one another, eliminating the need for unnecessary components and other potential points of failure. And we also knew our theme. So the purpose of our Rube Goldberg course is to inspire middle school age students to consider pursuing an engineering related field. So for each of our stations, we chose to represent a broad branch of engineering. For station 1, our civil engineering station, you can see that we all interpreted the constraints very similarly, incorporating bridges, tunnels, and trusses, the simple structures that you think of and that a 6th grade student would think of when they think of civil engineering. Moving on to station 2, which represents aerospace engineering, our solutions were a lot more varied due to the complex nature of aerospace engineering. However, you can see both Sam and I used sources of thrust in my balloon and Sam's hair dryer, and Matthew's design here represents a jet engine. Moving on to station 3, which represents computer engineering, we all collaborated very heavily on this station because we knew we would need a decline ramp to take us from station 2 to the exit. We also knew we'd be using our Arduino in this station to represent computer engineering, and we also wanted to use ultrasonic sensors. And each of these times, the ball hits an ultrasonic sensor, which triggers some kind of reaction. In this case, turns on an LED. Here moves a sliding bar, and here rotates a crevice. Our concept selection for station 1, while we completed both a concept screening and a concept scoring, our concept screening always reinforced the results of our concept scoring, and because the concept scoring is a bit more specific, we decided to only include that one. And as you can see, our concept scoring, unlike our concept screening, the criterion are rated, and we rated these giving the most heavy weight to the criterion that are most indicative of our customer needs, that help us reach those the best, and the lowest to those that do not contribute necessarily to its major functionality, but are still very useful and important to the overall product all the same. For station 1, we decided to continue 2 of the alternatives, Matthew's and Sam's, and because they had very similar scores on the concept scoring. So we built prototypes of both of those, and we contacted our customers that we had interviewed much earlier in the process to ask for suggestions, criticisms, and finally to ask them which design they preferred. And unlike what we expected, their responses to that question were very ambiguous. They enjoyed the detail present in mass design, such as the trusses and the nature of the tunnel. However, they enjoyed that Sam's design incorporated several structures in a very smooth, connected way. So we took that seriously, and as you'll see in our final station, we have 5 different structures that all connect very smoothly. Moving on to our concept selection for station 2. We only decided to continue one of our solutions for this station for several reasons. As you can see by the components involved in our solutions, they are much more complex in the first station, requiring much more time and resources to create. And so we decided that we would be better off to focus on a solution that we felt had a higher chance of success than to potentially waste time and resources on more complicated ones that might not. And moving on to our concept testing, we built a prototype of solution up here, and we found that the balloon was not a very good source of thrust. We decided that a decline slant and gravity would provide much better momentum for the station. So we altered that and we showed it to our potential customers who loved it. Moving on to station 3. Once again, we only continued one design because it heavily outscored the remaining 2 alternatives. We were very excited to have such a clear winner, and we were very confident that this design would be a hit. We built the prototype with 0 issues, showed it to our customers, and their responses were very unexpected. They did not feel that this station would adequately represent computer engineering. They felt that we had simply constructed some kind of electrical device that really didn't display what engineering was. And they also felt that students would not be able to apply this to the real world. So we went back to the drawing board and decided on a stoplight simulation for station 3, which you will see later in our project. Moving on to our failure modes and effects analysis. After analyzing this, we found several recurring themes. The first being the major source of malfunctioning was in the material. That material would, either the material that our structures were made out of would either break or deform, or the material that we use to connect our stations to other stations or to the board itself would malfunction in some way, such as the glue would not hold, etc. And our second most common theme was user error and misuse. And moving on to our detection methods, for material malfunctioning, we very heavily tested the materials that we chose to proceed with. We tested them in environments that were much more extreme than our Goldberg course would ever be subjected to, so we could be confident beyond doubt that we would not be putting our users at risk and that their machine would be durable. Our detection methods for our user error misuse involved making sure that our users understood how to take care and use their Rube Goldberg course. Just because these failure modes were a result of user error and misuse does not absolve the Lyman Group of any responsibility. We are still very responsible for making sure that these failure modes do not occur, because it is our job to educate our consumers on the product they're buying and make sure they know how to use it. Our corrective actions include continuous material testing to make sure we're always using the best one for our purpose, and customer outreach. We had relatively low risk priority numbers because safety was a top objective for us. We knew children would be working with this device and we did not want them to be put at any risk whatsoever. And our highest risk priority numbers were a result of mild user irritation or frustration. That would be a result of breaking points that might cause minor repair or replacement.
One of the tools that the Lyman Group utilized during the planning is 3D CAD modeling. So 3D CAD modeling is great because it's an early prototyping tool. It allows us to create visualizations of our concepts that are easy to manipulate. We can add features, subtract features, change around the stations how we see fit until we get an end product that we like. It allows us to create dimensions so we can see visually how much space each station is going to take up and whether we need to allot more space for one station or the other. Finally, for defining stations, it helps us define our boundaries. One of the most important parts of our Rube Goldberg machine is the connections between the stations. So how will civil connect to aerospace, how will aerospace connect to computer? 3D CAD modeling allows us to visualize and create a solution for these boundaries that we normally aren't planning for but are very important nonetheless.
We consider our product to have very modular architecture, and this was quite intentional. As you can see on our clustered schematic to the left, each chunk only has a small number, maybe 3 or 4 functions that it implements. And furthermore, we consider it to be a slot modular architecture because while each component connects directly to the pegboard, they do so in different ways. Some of our stations connected via dowels into the pegs and others simply with glue. The advantages of such a modular design include it allows us to easily implement variety in future generations of the Rube Goldberg course because it minimizes the number of changes that need to be made to components to achieve some kind of functional or aesthetic change. For example, a change to station 1 would only require changing factors in station 1, whereas if we had an integral architecture, it may require changes in station 3 or station 2. And our chunks follow a very logical pattern. As you can see, each station is its own chunk, as well as the Arduino, the servo, and the computer. And the flows between our chunks are also very logical. The flow of material, which we consider to be our ping pong ball, flows from the servo to station 1, to station 2, to station 3. And the signals and power flow from the computer to the Arduino to the servo.
Now we'll take a look at some of the later stages of our Rube Goldberg design process, such as the industrial design of the project, the assembly time, the cost analysis, and some things we would do differently if we were to do this again. First things first, we have industrial design, and our industrial design is important to us because we're working with 6th grade students. So, 6th grade students, as many of us know, are very, very low tolerant for the amount of time that they can just sit in a seat and pay attention. So, our first few industrial design features, such as the aesthetics and the time that it takes to go through the machine and the ease of use, all hit on this feature because we want students to be engaged with our product. Our last one is the real-life application, and that's actually one of our most important features of industrial design because we want students to see these concepts displayed in real life and in this Rube Goldberg machine. Next, we have our assembly time. Our assembly time is very based off of our symmetry and our hold down parts because we have many parts that are either necessary for both hands and needed for a little bit of manipulation and symmetry combined. So the symmetry in our product requires us to take down a little time, whereas our hold down parts actually increases our time to create our Rube Goldberg project. Now, we wanted to induce more one-handed parts, but we couldn't because of the amount of gluing that we needed to do in our Rube Goldberg design. So to create one of these Rube Goldberg machines, we took about 15 minutes of time. Our next assessment is our cost analysis. And we have our variable and fixed costs. So our variable costs tend to hit on our materials, and that's because we're not sure how many Rube Goldberg machines we will sell year to year. Whereas our fixed costs, no matter how many Rube Goldberg machines we will sell, they'll stay the same. So in total, we have about $400,000 in fixed costs, and our variable costs will vary from year to year.
Finally, after we were done with the project, we took a moment to reflect and think about some future improvements and critically assess ourselves. One thing we like to do is cut down on design phase inefficiencies. So some of these are focusing less on the station scope and more on how the ball will actually go through the course, where we should have been focusing on the concept of stations and what the end user should learn. Another thing we should have done was execute tasks simultaneously as opposed to iteratively. For example, we could have done some concept generation and final CADing at the same time, as opposed to doing it one after the other, which increased production time. One final thing is our constraints yielded an unreliable product. What this means is that it was not as durable as we want. We don't think it could survive in a middle school classroom setting. So one thing we would do for the product is physical improvements, more modular structures, increase interactivity, and more durable materials. Finally, we would wish we had a little more consistent team coordination, which would have made the entire process a bit smoother. So we'd like to thank you for your consideration for the Lightning Group Rube Goldberg machine, and we hope you have a wonderful day.